So hey everyone, so today is going to be like the third installment of machine learning book speedruns. So the book I want to be covering today is Approaching Almost Any Machine Learning Problem by Abhishek Thakur. And so what I really like about this book is that, or in general, like Abhishek's work, is that he's very clear with his code. It's very short, it's very simple. And he's definitely like a practitioner. Like I think Abhishek became famous off of doing a bunch of Kaggle competitions. He works at Hugging Face now. He streams regularly. And in general, I just find his code very, very clear. And so we're going to be going over this book. Like I have a copy of it. I'd highly recommend you check it out. And so I'm also just going to be like skimming through the book and discussing what I think are some of the most important ideas in it. And so let's see here. So we're really going to be talking about a bunch of stuff like setting up environments, supervised, cross-validation, why it's so important, how to evaluate metrics, how to arrange projects, feature engineering, selection, how to pick good hyperparameters, and then just cover a couple of use cases like classification, segmentation, text, and then end up with assembling and stacking, and maybe some more thoughts around how to reproduce code. And let me make myself a bit bigger. That's a bit bigger, yeah. And just in general, how to do model serving, so how to deploy stuff. So the book really starts off by saying, okay, look, one, you can get mini conda. So mini conda is a smaller version of conda, which is like lets you create Python environments by having a YAML file. So you can say conda activate some environment name, like let's say we can call it approaching almost any ML problem, or you can create it with a specific YAML file and then activate it. So this is what I use quite a bit, although recently I've moved towards just using Python VMs. And so like we sort of seen this figure before, like I've drawn a similar one. Uh, but basically when you're thinking of like what is a supervised learning data set, like imagine you have like the features are your columns, and then different examples correspond to your rows here, and then features are, oh, oops. So the features here are the columns. And then the targets are sort of like here, their own thing, and there's like one target for each example. And this could be, you could have multiple targets for just one, but you know we can deal with that problem later. Um, so there's sort of like two main ML problems, like at least in the supervised setting. One is classification, so it's like you're picking a category, or regression, which is you're picking a value. So let's say this could be between 0 and 1,000, and then this would be, you know, 0 or 1, for example. So you could have like still like a lot more. So clustering is like an unsupervised technique, which is you don't have labels. You're just trying to figure out which examples look alike. And then there's also various techniques of doing clustering, like PCA, which is reducing dimensionality and stuff like that. So I don't want to talk too much about this, but you may have heard of the MNIST dataset. So the MNIST dataset is probably the most famous machine learning dataset, I would say, and it's essentially like handwritten digits. And so the task is here, like, so it looks something like this, and the task is like, well, a computer needs to look at this and figure out what is the, like, what character is this? And so if you imagine like an image, like if it's a grayscale image, then this is, you can map this to like a 2D matrix where in each value you'll have, for example, like let's say if it looks like this, right? So basically one where it's black, and then zero where it's white. This would be like a digit one, for example, and you want to be able to turn this into saying, okay, this is one. So this is sort of like the simple MNIST problem. A lot of times, like when you're fetching a data set, it really is important to just know how to create I think a data loader, and how to like if you're doing a data loader. I'll just quickly show you. Actually, maybe I'll write the code for it. It'll be simpler. So when you're thinking of a data loader, let's say you have a data loader, right? So like what is it? What does the data loader actually do, right? So there's a couple of stuff it needs to do. So one is, for example, it has like some location where it is, right? Maybe it has like some sort of like max length, like a number of examples, right? Maybe it has like some number of features, f. And then sort of like what are some functions that you would need on this? Like, well, one is, for example, just getting the next, like let's say getting the next example in the data set, right? So for example, this could be, you know, like let's say all of the examples are self.x is equal is in some so some list, for example. And then self.y is also equal to a list. This is actually a list of lists, right? And then next would basically say, okay, so let's say the current index self dot current index equals current index. And what next basically needs to do is you would say, well, current index plus equal to current index plus 1, and then you want to say return x of current index, right? So this is sort of one thing you may want to do. Another thing you may want to do is sort of split your x and y. So for example, this could be define a split train test, for example. So typically in ML, you'll have like, let's say 30% of a data set let's say like 70% of a data set in training and 30% in test. So what you can do is, for example, you can say import random, and then you say random, so coin equals random dot random, and basically if coin is less, if yeah, so if coin is greater than 0.3, and then if coin is greater than, actually no, I'll do it this way. So if coin is 0.7, and if coin is yeah, so if coin is greater than 0.7, then you basically want to say like, let's think about it this way. So so yeah, so this gives us a percentage, right? And then I guess like one trivial way to do it is just to say uh, x of 0 to, so let's say coin, so number of train, right? So this is going to be uh, coin times length uh, length of x of self.x, right? And then what you want to say is, okay, well, I want to put all of these examples as part of my training data. So let's say you have, this is train data. And then test data. Well, actually, it's a bit more than that. So this is going to be x num of training data, and it's also going to be y 0 to number of train, right? And then test data will be x of number of train to yeah, so basically everything, right? And then y number of train. And then what you do is you return train data test data. So this is sort of a, like the reason I went through this is because this is sort of a super common pattern, like where you know, you're going to have something like this, and then eventually in your ML code, you're going to be doing something like, okay, well, you have some sort of like model, right? So you'll have like something like class, like import torch. Then you're going to have a class that says like my model, for example, and then this is a subclass of neural network dot model, and then self. You have basically your init, right? And then you have your so this is, let's say, self.x equals x, something like that. And then you have your forward function, right? So this is how PyTorch does things, and you can say something like return f of x. So let's say this is f, and then so it's like some function, right? But then actually when you're doing model equals my model, right, you're gonna essentially then do model dot fit on split, uh, like let's say you have your data equals split train test. So you're gonna have train data and then test data. And then what you'll do is you'll say, okay, well, I want to say model dot fit test data, and then model dot predict sorry, test data, and then model dot fit train data. This is a super, like what I just showed you is a super common pattern. Like even you'll see this a lot in the default data loaders in NumPy, the default data loaders in TensorFlow, the default data loaders in Hugging Face. Like almost everyone does something like this. So just if you know this pattern, it's kind of cool because then if you have your own textual data set, and as long as you can turn it into like the sort of like array of arrays, you can just do something like this and have a good time. So let's see what Abhishek does though. So what Abhishek does is he says like, okay, well, I'm prefetching it this data set called OpenML, and this data set is coming from scikit-learn. So this is what the sklearn here is. And it's like, okay, well, you can also plot images in matplotlib, where you can just give it an image as pixel values, right? That are reshaped to be 28 at 28 by 28, so just 28 by 28 pixels. And then you also want to map the values to be gray. Um, so you can also do some other stuff, like here, for example, they do TSNE, they'll have some other visualizations. And I think sort of first important idea in the book is cross-validation. So what is cross-validation? So I really like this definition because I haven't seen it before. And so the one-liner that Abhishek gives is cross-validation is a step in the process of building a machine learning model, which helps us ensure that our models fit the data accurately and also ensures that we do not overfit. So okay, great. So it's a technique that prevents you from overfitting. So what's overfitting? So okay, so before he explains that, he goes like, okay, well, first he's going to use this wine data set. So he uses wine quality, like looking at the residual sugar and the volatility and the citric acid and the density and the pH. Notice how all the wines have low pHs because acidic wine is garbage and has like similar alcohol percentages here. And it's like, okay, well, let's see. So he comes in here. Another thing you may want to do with the data set is shuffle. So as in like pick a random example as opposed to just hard fixing it. So that can be changed in our code for training and testing by, what we can do is essentially when you're getting the next, like you could pick a random value instead of picking the next one, and it should do something similar. Okay, and so we want to make a decision as to like, is this wine good or bad? And what we're doing is we're turning a lot of these, like a lot of these numbers, into sort of like here. So like we can create a quality from 0 to 5. So the name of this book is the Approaching Almost Any Machine Learning Problem by Abhishek Thakur. It's a very, very good book that goes over good programming patterns to write machine learning code. It's almost all code. There's barely any math in this book. All right. So, okay, great. So we're doing this where, okay, we have our train accuracy, we have our test accuracies, right? We start with 50% accuracy. Then it's like, okay, well, we build a decision tree classifier from scikit-learn. We have some columns that we label. So there's also dataset loaders and pandas that can do this for you. But I guess here it's like specifically picking the ones we're interested in. Yeah, so notice this here. So you have this DF data frame. So data frame is basically an abstraction that pandas created to make it easier to work with tabular data. And essentially, you basically give it a list of columns that you want, and then it just trains on those. After you fit it, you get some predictions, and then you want to see how good your predictions are by measuring your accuracy. And then you append all the accuracies to a list, and you create a chart of it, and you should be good to go. So we should have a list here, for example. And okay, so for different values of max depth, and it pretty much looks like when you increase the depth, what ends up happening is that our training accuracy increases like very quickly, but the test accuracy doesn't increase as much. So what is this telling us? So this is telling us that, okay, well, it somewhat feels like our model is too complicated. It's like memorizing our data without actually doing a good job at the test accuracy. At the test accuracy here, which is what we care about. So this is what we care about here. So great, so great. So this is a pretty, I think, common explanation of overfitting, and it gets back to this like like this philosophical hypothesis called Occam's razor, which is essentially the simplest explanation is the simplest. Like, as in, like I don't know, I came back from outside, and I'm soaking wet. Well, the most likely, and let's say I live in Seattle, like the most likely explanation is that it was raining. Whereas if I was in San Diego in August, like that's no longer a likely explanation. maybe I fell into a lake, but there's other more likely stuff like I don't know, like I fell into a puddle, like I was going for a jog. So there's definitely more likely explanations, and they heavily determine like what is the truth. Um, so let's go over this. So when we talk about overfitting, there's a kind of cross validation which we call like the holdout set. So essentially, what we do is here. Where is it? Okay, so let's see, where is it explained? Samples, training and validation. Okay, yeah, I think this figure explains it. So imagine you have a data set and you basically randomize the rows such that the order doesn't matter for the model. And then you split this into k equal parts, right? So this is called a k-fold. So you're basically making your data set like 5 times smaller essentially by doing this. And it's like, okay, well, we can certainly do something like this. And where's the points? Yeah. So for example, here, distribution of labels. Okay, standard classification problem. Holdout, time series data. So where do they actually do the? I'm looking specifically for the classification that he ends up doing. All right, apologies. I'm just like looking for it because I'm skimming very very quickly. Okay, yeah. So like imagine, like I sort of like this, like in when you're doing this is a neat trick by the way. So when you're trying to figure out, for example, let's say you want to do k folds, like well, how would you create something like this? Imagine that you're flipping a five-sided die, right? And then after flipping each five-sided die, you assign an example from the data set to a fold. And this is sort of like a very simple way. I mean, they're not going to be exactly the same size, but they're roughly going to be equal to the same size, and that's like just a very simple way of doing this. And you can flip a five-sided random die by doing something like random dot random times five. And then something like this. Right. So there's all sorts of tricks you can use here for choices and assignments that make your like programming life easier. Let's see. I'm not a big fan of the explanation here. Certificate number of bins. So in stratified k-fold sampling, we first divide the target into bins, and then use a stratified kit in the same way for classification. Okay, basically this is like a heuristic to pick k. I've seen the most common one is k equal to 5. I don't know why I see this all the time. All right. So this is interesting. So when you think about like is a model good or not, often like we look at accuracy, which is the number of predictions you got right. But then there's other interesting ones that I think are worth discussing. So let's just go over them quickly. Here. Right. So imagine that accuracy is a function, right? And it takes in the true predictions and the actual ones. So you're basically going to do is every time they're equal, you increment by one, and otherwise you just divide by the rest, and this gives you a number. Scikit-learn also has one, but you could also do the same thing with true positives, for example, like which ones are actually positives, with true negatives, with false positives, false negatives. So all of these are essentially like these two liners. There's a simpler way, I think. Is there a simpler way to write this, like in straight up one line? Let's try accuracy. I think this is probably pretty simple. I think there's probably a one liner with maps, but it's not very important. So precision and recall are important. So let's talk about these briefly. So what precision tells you is that out of the examples that you said were positive, how many are actually positive? And then recall tells you how many of the actually positive examples in the entire data set did you find. So when like let me give you a use case for each of them. So let's say for example we're precision, right? And I'm annotating some entities in your email as being important. Um, the precision here matters a lot because like if I'm annotating stuff in blue but it's garbage, you're gonna think the experience is really bad. So it's important to have high precision. Whereas like let's say if I'm building a classifier that tells you is this email you have a flight or not, it's very important that I get the recall high because if you're now dependent on my app to figure out your trip details and if you miss your flight, you're gonna blame me. So it's not just like a percentage issue in your model. It's like you have a real negative dollar impact on someone who's gonna hate you for life for making a misclassification. So recall is very important in these cases. Yeah, so it's pretty common. Like generally, when you have some sort of like binary classifier, you're gonna make a prediction, which is a real valued number, and then that precision is gonna have like that threshold you can control. You can say, well, if it's more than 0.5, then predict positive. It's yeah. So here it shows up here. So I basically is the threshold, and basically, as you can imagine, the thresholds have a big influence on what your precision and recall should be. Um, and essentially you want to have a curve such that like when you're trying to think of like what's the optimal class, like well what's the optimal trade-off, generally you want to optimize for something called like the area under the curve, which is where the curve is this precision and recall curve plotted as a function of the varying thresholds, right? So basically, ideally, you want to find a good trade-off between them, and this trade-off could be just dependent on your specific problem, in which case you would pick a specific point under this curve, or if you don't know, you can just like look at what maximizes the area under the curve, right? So one way to also balance this out, like if you want to have a sort of trade-off between precision and recall, you can use the F1 score. So it's basically what's called a geometric mean because it takes the product instead of just the addition and then divides them. And so ideally, like higher F1 is usually better. So high F1 is great. All right, a whole bunch of metrics, calculations. Oh, sorry, I made a mistake with the area under the curve. I apologize. So your plotting is not precision and recall. You're plotting the false positive rate alongside the true positive rate. And so you're going to end up with this curve here. Okay, yeah. And so this is sort of how to interpret it. So oh, interesting. Yeah. So one thing to keep in mind about machine learning is if you have a model with 0% accuracy, like that's actually amazing because if you now do the opposite of whatever your model says, that means you have a great model. The worst model is actually a coin flip. So the worst models make predictions that are around zero point 0.5 all the time. Um, so yeah, I mean, let me just the rank higher. Yeah. All right. So here they also talk about the log loss. Like when you're thinking of a binary prediction problem, generally what you'll be doing is something along the lines of uh, here, like this shows up basically like another way to interpret. Like this is easier to interpret, like in if you look at the math actually. And I do cover it extensively in the other book Speedrun, specifically the 100-page ML book one. But the main idea is this is sort of like you can think of it as a prediction that works when your prediction is positive versus when your prediction is negative, that you're always taking the correct distance to the target. So a formula like this, you can pretty easily like test out here. There's all the code for it. I know what macro precision is. Precision, weighted average position. All right. So confusion matrix is interesting when you're trying to debug a model. You can basically plot out the number of like basically plot out all the possible labels in the data set with all of your predictions. And this gives you a visual idea of like maybe there's a specific subset of the examples that you're getting wrong, and so that can either maybe you remove it from your data, or maybe you like figure out how to solve for that. Maybe you need some additional features. So those confusion matrices are generally very useful. It looks like scikit-learn has one by default. I also really like the one that Fast AI has. Like they have a confusion matrix that where you can even hover and see the actual examples that were misclassified. I think it's very powerful. Like probably in Matplotlib, but we just need like a bit more programming to get this done. So, however, like let's now discuss like a different set of use cases. Let's say we're talking about rankers. Now, like instead of talking about like precision or recall, like typically we talk about these metrics like precision at k. So what do these metrics mean? So here, precision at k. So first off, well, if k is equal to zero, then okay, then we return zero. So basically, imagine that you're predicting k things. So this could be, I'm recommending 4 articles for you to check out on Google after you Google automatic differentiation, for example. And so okay, great. So we're gonna have like these 4k, like we're gonna have k predictions, and make these predictions a set, as in we don't care about the order, and then make also the actual values a set, see by how many times they intersect, and then return the total number of ones in common. However, you may have guessed that, well, is this a good metric, right? Well, not really, because the let's say I show you a list of stuff in Google. What you get for the first result is a lot more important than what you get for the last result. And so it may make more sense to weigh this example more than others in your loss function. So let's see, are they going to do this here? They're going to do this. Average precision at k. I don't think they do. Wait, do they? Max average precision at k. Okay. So we append all the values, and then we return the sum of the values over the length of the values. I forget them with the name of the metric. It was the discounted cumulative. Yeah, so this is this is more closer to the metric that you want, but you can think of it as a way like the log is basically right. It's just a way of turning exponential values into non-exponential values. So think of this as you want to make it so the more important stuff gets ranked. The top level predictions are ranked higher. So think of it like an exponential like multiplier to this. All right, so this is all good. So yeah, so again, like I mean, here, like I like how he starts off a lot with metrics because these can seem like fairly ambiguous, but it's like a good way instead of before starting with machine learning, just like with these metrics. Like when you're trying to find like the error, like really your true value minus your predicted value, but actually it's more of a function of your true value and your predicted value. So one way is just the straight up error, the other is taking the absolute error, another is taking the squared error. And so you can think of it as like more generally, like let's say if like I'll show you an example. So let's say I want to like you have like some sort of function called your error, right? And so what does this do? So it has like some f and it has like some x and y. right? And then you basically want to return uh, f of f of x on y. Right, so this is gonna seem very abstract, right? But let's do an example. So let's say your f was defined, let's say apps of f, and what this does is it returns basically the absolute value of the arguments of f. So basically, think of this, something like this. And so this gives you like a good pattern where you can think of like, okay, well, I can just pass in like a function that does this. So basically, like here, sorry, this would be more like uh, arg v1 minus arg v2, for example. All right, so this is a function, and then you can just like pass this in, and this is like a good like functional approach to dealing with these error functions. For example, if you want to do squared error, then this would change by just being like define a square, right, of f, and this is just going to be a return math of. Uh, so actually, no, it's going to be like arg v of one to the power 2 minus arg v of 2 to the power 2, and then you take the something like this. May have made a typo. No, squared loss is that. Sorry. Oh yeah, sorry. It's just yeah. So I apologize. So it's just this. Sometimes I get confused with these. Right? And so you can also imagine, well, like why not p, right? Like then you could have like the power, and then this is p, and then you can take the arbitrary p loss, where you can just say like p is an integer. Okay, fixed it. Yeah, nice. Oh, I see. Yeah, so it's lowercase. It's just like it makes the point clearer because we don't. But to be fair, like floating value losses could work just fine. So maybe we don't even need this. In all cases, I think we can just get back to the book. Where was it? Going crazy? All right, so they have like a billion different definitions of errors. I think this is probably not as needed, but I think it sort of shows you some good habits, right? Like, look, this is a good comment, right? You don't want to write like comments in your Python code. Then it does something simple and returns it. So you're gonna have like these metrics like everywhere. So okay, so great. So we're done with metrics now. So what does a typical like open source ML code base looks like? So you have your data, you have your code, you have your models. So this is basically you would say like model.load model.bin. It's a binary file. You don't read this. And then like this is can be called notebooks or examples, which is like where you're doing your code. Your README because that's very important. That's the first thing people see. And license is like basically don't steal my IP, right? Like basically you wanna, in case you are building something that you think is going to be very useful, you want to make sure that you get credited for it. All right, so let's see. So here, for example, they have this run, create a basic model. Okay, so we're loading. Let's look at this. So we're loading data. We're creating our folds. We're dropping. So we're dropping the labels from the data frame and adding them to our Y. We create a decision tree classifier. We fit it, and then we predict on the validation set. We keep track of the validation sets, and once we're done, we dump them, and then we run it over 4 folds. Oh, interesting. Interesting. I didn't notice that here they're specifically looking at the fold. So where's the fold used actually? It's only used Is it used here? Is not. Fold, fold, fold. Where is it? Oh, interesting. Yeah, so it looks like it's here. Okay. This is all cool. Yeah, like this is kind of interesting. Like, I need to do a separate stream about how everything is a list in a dictionary in Python. But like, look at this. Like, let's say there's two different models that you want to try out. Well, like you don't want to like copy your code twice, but you may want to just set up a config in some sort of dictionary. So the key here is going to be okay. Well, I want to use Ginny, this decision tree Ginny, and when that's the case, I want to use a decision tree classifier with the where the criterion is Ginny. Otherwise, I want to use a decision tree classifier where the criterion is entropy. So let's see how this is used exactly. So here you have this models, models. Where is the models, 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 models. Yeah, so you're interesting. Like in the parser itself, you're adding like a model. So this is a very common pattern as well. And then yeah, you're actually passing it here directly. And then so where is it used? So in argparse, model is equal to args.model. So where is model? Model models.dispatcher is models model. Yeah. So this is where the model is being fetched. Like just think of it like a key value store where you're storing the metadata that you need. But again, very common pattern to do this. I see this quite a bit. All right. Oh, interesting. Okay, so there's like all sorts of variables. Sure. Like a lot of this comes down to how do you like given a data set with like these categorical values, like how do you turn it into numbers, right? So this is all very common, like in the data frame library, but I didn't know Scalar had pre-processing. And it's interesting that they also have their own label encoder. And I will say that Keras and PyTorch also have their own. They're all good. So it's really up to you, like what you want to be using. They all kind of do the same shit, as far as I know. Okay, so a feature matrix, sparse CSR matrix. Yeah, this is a common trick, but essentially, like if you have a giant sparse matrix, like instead of thinking of it as a list, think of it as a dictionary where the indices that you have are the ones that are not empty. So it basically, and then you can do matrix multiplication or whatever you want uh, with these sparse matrices. So that's all fine and good. Yeah, so he also talks about one hot encoding. So one hot encoding is basically like if you have labels, like let's say you have a class 0 and a class 1, that you could turn a class 0 into like a dictionary that looks like this. Let's say it was 0, 1, 2, and so this would look like this. This would look like this. And then this would look like 0, 0, 1. Out of curiosity, let's see if I can do this. Let's see if I can do this quickly. So let's like try to implement the one hot encoder, right? So let's say define one hot. Right, so what is this? So what is this gonna take, right? So it's gonna take in an example, and then it's gonna take a max number of labels, right? So basically, you're gonna say, okay, for basically you want to create a list. So basically, a label like example label. You want to create a list, and this is a list that's 0 for everywhere to the this. And then you basically want to pick the specific index that you want to make 1. All right, so basically you could say, uh, well, actually this isn't going to work. So you actually also need the examples, I believe. Let's say you pass this example and then example. Um, so then what you want to do is that you want to figure out, let's say you want to take a set of all the examples. So let's say you have uh, like number of actually no, we have that in the max labels, right? And then you basically just want to return example label. Here, let me do this. So example label of basically your key is equal to 1, and then you return example label, and then you do this over all of the examples. So you basically just make the one element that you care about be equal to 1. So okay, this is all fine and good. And so now, okay, we're going through this. And they're doing it like, they can do some reshape and stuff. So you can also build your own reshape libraries. Check out the data science from scratch speedrun if that's interesting to you. Um, yeah, so previously unseen labels like nan, 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 the Batman issue. So there's many ways to deal with nans. Like one way is to remove them, one way is to impute them. Imputing means take the average value of the missing features. So there's like a bunch of ways to deal with this. All right, so here they're using Elusive regression model. It's almost identical to what you've seen with the decision tree. Like print the metrics, print the AUC. Yeah, see here, this is what I was talking about. Like just make all the NaN values a none. Like make it an actual category, for example. This creates issues because then it becomes like a thing you can predict. So you have to be careful about that. So this is like called bucketing. So like check this out, right? This is a dictionary. And so what you can do is that let's say you want to map income in a data set to just high and low. What like so that's like like that's a continuous variable because income can go from 0 to a quadrillion or whatever. But let's say you just want to say, okay, well, if someone has less than 50K, they're poor, and they have more than 50K, they're rich. The way you would do this, you create this dictionary, and then you can pass this as a map to your data frame, and then it'll just basically do a filter. And it's actually one thing I really like. I'll show you this trick because I thought this was really neat, and it shows up quite a few times. So let's say you have so you have your list, like a list, and you have like -1, 2, 3, 4, 5, 12. And now I want to say, like, I want to return a for greater than 3. Does this work? How do I pass in a filter? Array filter. Okay, so I want to pass the filter, and so okay, I have a function. Okay, it's going to be a bit more involved, but okay, let's say define a fun. And then this takes in number a, and then if a greater than 3, return true, else return false, right? So we have some sort of function like this. So then what you could do is you could say filter of a list, fine. Why is this not iterable? Oh, it's the other way around, sorry. So fun, a list, right? So it gives you a filter. Let's say now we want to say a is equal to this filter. Now print a. No, that's not what we want. We want to actually return. Oh, I see. It becomes an iterator. It doesn't become a list. Okay, so then we have to say for a val in a, print a. Huh? What's going on here? Okay, can I turn this into a list? Okay, it's empty, but why? I mean, yeah, I like that it's passing in the not the lambda function. So okay, let's see. So it's gonna return all even values now. This is gonna work. Right, so then now they just say result. Okay, and then you want to print list of results. Okay, that worked. Okay, so now instead, imagine this could be x greater than 3. And it returns like what you expect it to. So this is very useful, actually. Like I found this pattern useful whenever I'm pre-processing some data, like having these filters or if conditions here. But remember, this could be any function, right? So just do whatever makes sense here. Okay, so here they're doing a couple more stuff. So for example, he's saying here he's actually more explicitly engineering some features, which you could do. So like list of some numerical columns, like create more of this. Obviously, like with deep learning, like you don't need to do any of this. You just like feed it in the whole thing, and it just magically works. And then here, so he's using this model here called XGBoost, right? And I would imagine -1 means like as many jobs as possible. And how does this work exactly? So then you say like model, and then you fit it, and then it works. So let's just quickly check out XGBoost because so what gradient boosting really is that you can think of it as you have a model that you train on some data set. It's going to make some mistakes. And then on those mistakes, you train another model to just classify those mistakes, etc. And you keep going. So this is a very, very useful pattern as well. It's used quite a bit in like all of the Kaggle competitions like XGBoost and decision trees. Right, so this is a deep model in this case. So we just have so yeah, I believe this is Keras if I'm not mistaken. Yeah, it is. So yeah, so you just have like this relu activation function. You have dropout, which is a way to regularize some batch normalization. Then you do this again, and then you have a softmax, which lets you make predictions, and then you actually have your final model, and then you compile it with Atom, which is a pretty popular uh, uh, pretty popular optimizers that uses like second order derivatives. And then the binary cross entropy means basically like binary classification. All right, so this is we saw this before, right? So this is the target times log of prediction uh, plus 1 minus target times log of 1 minus prediction. This shows up quite a bit. All right, so this is all cool and all. And yeah, and I think one thing he mentions here is that if you have a GPU, this just runs really fast. And you have a GPU by default in Google Colab, so make sure to check that out. In case you don't know where it is, doing GPU programming at this point is literally here. You just go to edit, you click notebook settings, and you pick a hardware accelerator, you click GPU, and that's it. Like this is how you do GPU programming these days if you're using a very high level library like TensorFlow or Keras or PyTorch. So in all cases, like we can keep going. And here they okay, he's gonna talk even some more about feature. So you see, like I mean, a substantial amount of the book is actually dedicated more towards feature pre-processing and metrics. So that's sort of the hard part. The model part is actually fairly simple. You can usually copy paste it. This is generally the part you can't copy paste. And here, like he does stuff like percentiles. This is all good and great. Okay, feature selection. Uh, yeah, so this is interesting. So, like, when you think about like what's the most useful features, it's the features that sort of change the least. Like, let's say, for example, you have a data set that's like only has men in it. Then having men as a feature is not very useful because it's not gonna because like your labels will not be a function of that at all. So it's just like useful to just better to remove it. And one way to do this is by this idea called the variance threshold. But another way is basically you can compute the variance for all of the examples, and then keep track of a certain threshold, and then use that. So it's easy to actually code this one function. Okay, this is all great and good. So let's keep going. Yeah, so it's also important to keep track of hyperparameter optimization. So this is another useful pattern here where you could have your parameters be in a dictionary, and then you iterate over this dictionary to be able to figure out what's the best model. And so, for example, what you would do here is, okay, you're saying, okay, well, for A in range of 1 to 11, for B in range of 1 to 11. So these are your three hyperparameters. And then change your models and basically train all of those models. So you train 11 times 11 times 11 models, and then you keep track of the best one. So really, hyperparameter search is a form of brute force search, but it's actually pretty helpful and is a very commonly used trick. So okay, I like this. Like, so you see again here, like imagine like anything that's a list is also really implicitly like a dictionary, or it could be like in an XML config or something. So it's also useful to separate your code from your data. All right, so moving on. Initialize entropy, quadratic weighted kappa. Kappa. Okay, you talk about SVD and the scaling, the kappa score. All right, here we're talking about minimizing loss functions. Okay, what is this table? This looks interesting. Yeah, so I guess like just talking about the various like there's better figures I think than this one. But it's just like something to keep in mind. Like these are sort of like the things that you need to change. Like, well, how many forests do you have? What's the max depth of one? Like, what's the minimum number of samples per split? In logistic regression, this would be like, what is like, are you using L1 or L2 loss? And if so, by how much are you weighing it? For k nearest neighbors, you have a number of neighbors, you have your p. So these are typically all hyperparameters that you need to try out to see what actually works best for your data. So it's very empirical. So looking at a specific subproblem, like we're going to take a look now at image classification. And so it's just important to consider that like an image is actually just like a list of pixel values, right? So you can even treat this as a list if you wanted to. And a lot of early image work do this, but it's not ideal because the order of places matter. You can create your own image data set by essentially opening images from your file system and adding them to and making them a matrix. So here you'll see, well, we're resampling images by bilinear. So this is just a way to upsample the quality of an image. And also you're saying here, look, we're resizing this images to 256 by 256. So Ravel is flattening it and making it into a list. And once you flatten it into a list, you can pass it to a fully connected neural network and just make a model that does a prediction on it. So in this case, they again use a random forest classifier with as many jobs as possible. That's generally what -1 means here a lot of times. And they keep track of all the folds and the AUC and just pick a good model. All right. So one of the important ideas here is that when you're doing a convolution, you could dilate it. So that way you're getting more global features within the same convolution. Max pooling is a way to aggregate data. And if you look at the early like models that worked well on ImageNet, it was really this AlexNet model. And it's nice like when you look at the existing PyTorch code, like just to see like how simple these things are actually now to implement. And I do cover these and how to implement vision models from scratch, like one of my videos on YouTube. But essentially, you set the number of input channels, output channels, and you see like these always match like 96 to 56, 56. You pick a kernel size, and the kernel size here becomes smaller. You have the stride, which determines by how much are you jumping, and your padding, which is basically how you deal with like when your convolutions don't map exactly to one another. So you have all of these. Then generally you always have this dense layer near the end, and then another dense layer with a dropout. And this is really where your prediction is going to happen. And this is obvious if you look at the forward pass. The forward pass here is, I believe, this should just be the here. Yeah, sorry. So this is the last layer, and then you take a soft max over x, and this gives you like the actual prediction that you're going to make. So the most common data like library to work with images is PIL. So could you recommend a good resource to set up my environment to do this in machine learning? Yes, I can actually. So I think the two best ways, if you're a total noob, just use uh, Google Colab. So go to collab.research.google, TensorFlow, PyTorch, everything's pre-installed here. This will be like the easiest way for you to get started. And after that, if you want to just run this locally on your own machine, I would recommend you check out Conda. And then in Conda, what you can just do is check out the very first chapter of this book, the Approaching Any Machine Learning book, and it goes over how to activate it. But I'll just give you a sneak peek. You can just literally say conda create a specific environment name, like let's say tutorial, and then with a specific Python version, and then you would just say here like, okay, download TensorFlow, download PyTorch, get everything working. I will warn you though, getting stuff set up on a GPU is a bit more complex, which is why if you're really just getting started and want to have fun, I would highly recommend Google Colab. It's actually what I use for my quick experiments at this point, because I can share this link with other people. Like let's say I'm going to share this with you guys later. I can just add this to my YouTube description. So it really makes your life a lot easier if you're a beginner. So I highly recommend it. So anyway, here, where was it? Going up. Okay, so here we were at 198, I believe. We're discussing images. Yeah, this looks like an vision model. So look, so even PyTorch has some pre-trained ones. Like it'll have like ResNet, for example, which is a very common architecture, like 18 blocks of it. And then the forward layer looks like this. You're taking like the cross entropy, and then you can have like some sort of command line interface where you can pass in like which device you want to run this on, like the CPU or the GPU, the where your data is, how many epochs, like how many times you're going to run through the example, and then everything just works nicely. Text classification is a bit different. So in text classification, like let's say the most typical example is like let's say finding the sentiment of a piece of text. Like here, for example, what he's doing is looking at the number of positive words, number of negative words, and if there's more positive words, then it's positive. Uh, a very important problem in NLP is generally you're given like bodies of text, so you want to tokenize it, where essentially what you want to do is count, like basically split up all the independent words, like what's a word, what are word pieces, etc. So this is all very common. Hugging Face even has facilities to do this really fast with the Rust library. And so once you do this, okay, well you can set up, you can start like working over this tokenization as a feature for some machine learning model. And this is here what they do here. One way to sort of make this a bit more advanced is that you can basically look at this metric called TF-IDF, which is essentially making words that don't appear very often in the corpus look more surprising and should play a bigger role in what your sentiment should be. So the idea here, it's similar to the coin flip example where the worst thing a classifier can do is flip a coin. So the more something is unique in your corpus, the more likely it is to be an important feature for your classification. All right, so you can also do some stuff like cleaning up a text, like removing all the punctuations with some regex. So these are all very important to learn about, like the pre-processing stuff. And this is, I think, also pretty important. Like here, I think they're gonna turn like a sentence into a vector, and then you can like load these vectors and use them for something else. And the important thing to know to remember here is that like machine learning models don't actually understand what a word is. So they understand what vectors are. So you want to turn sentences into vectors. So one way to do this is just like a bag of word count. But ideally, like you end up creating these embedding matrices here, and then you can feed these embedding matrix to some sort of like neural network. And this is like a simple like what's called the bidirectional LSTM. Like I've used this before for a problem called part of speech tagging, which is essentially given a sentence like I am Mark, like figuring out like this is like this is the like this is a like a subject, this is like a proper noun. So sort of like the proper grammatical role of a sentence can be used as a feature for other models. And then once you have this LSTM, you can have like this a fully connected layer here, which then actually just makes your prediction for you. So this is all very common, and the way the training and testing works is almost identical to what we discussed before. Um, so here, for example, you can notice here there's this to device. So in PyTorch, you can explicitly send stuff to your accelerator here, like as in this is your GPU, and if it's by default CPU, then it's just going to keep it on the CPU. And then you take the logits with loss. Again, this is a binary classification problem here. And I think we're good to go, right? So here, for example, another way is like well, you can even load these vectors instead of you training them yourself, you can load them from someone else. And then again, when you're training something, you would basically fit on this data set across multiple folds and then keep track of those folds and return something. Yeah, but turns out like, LSTMs, bidirectional LSTMs, I think are an easy model, but nowadays people use like BERT transformers. If you're using a BERT transformer, you can go ahead and download like a pre-trained transformer from Hugging Face. Like this is the Hugging Face transformer library. So you can get something from there. Oh yeah, so this is the BERT data set that I talked about. So this is slightly a bit more cleaned up, but you notice here like, well, there's a review, there's a target, there's a specific tokenizer and a MAC length. You can get an item, which is basically encode something additional and then put and then return. Uh, what is the ID of the sentence? What's masked in it? What are the targets and what are the token type ideas? So these are all things that you can do. And even here, like let's say this is all you just see like how a lot of this becomes like almost like config driven development, which is why I've made the case that a lot of modern machine learning development has turned into DevOps. And so the quicker you can experiment with stuff, the better machine learning engineer you're going to be. And having good configs will let you do this because that means you can sort of scale out running your experiments and have experiments running while you're sleeping. And that's always like a good position to be in. So another thing to keep in mind is ensembling is let's say you have 10 classifiers that you've trained on the same data set, and each of these classifiers are better than a coin flip if you aggregate them. This is like it allows you to have decisions that are pretty good. So one way to do it is to take the mean prediction. Another one is to take voting, like who voted for the most. Another is to take a ranked vote, for example. So you see how this quickly turns into almost like a political, just way to aggregate models. And so let's see here. Okay, yes, yes, sure. Yeah, so what's stacking? If you have a correct cross validation, keep the folds the same throughout the journey of your modeling task, nothing should overfit. So you divide the training data into a bunch of folds, you train a bunch of models, you create full predictions. So you use the full predictions from these models as features to another model. This is now level 2. Yeah, so here the idea with stacking is that you keep track of the places where your models didn't do a good job, and then you train new models just on those examples. So that way you basically create a way for people to specialize. Finally, I think one interesting point here they talk about is like how can you make your work reproducible, right? So the way I've been doing this lately is I just share a Google Colab notebook with people because it's just so easy. But more, I guess, like if your compute can't run on a single Google Colab notebook, as most interesting problems don't, you can do this via Docker. And so you can basically create a Docker notebook that essentially creates an environment such that as long as people emulate your environment, they're almost guaranteed to get the same code as you. So the way you do this is that you can basically create a Docker file, which is responsible for setting up an environment, downloading some data, creating some directories, and then running a model. So think of this as like a mini shell that you want people to replicate. So you may wonder, like, let's say the way I've traditionally done this is really well, you can give people a bash RC, and then, as long as they copy your bash RC, they get similar stuff. So this is very similar, but just like a way for people to copy your bash RC or download it automatically. Right, so let's see, NVIDIA has a Docker runtime. Okay, that's great. And so you can run this model, you see interesting, like on a specific number of GPUs. And then you can serve these models using Flask. So Flask is sort of like the simplest uh, way to turn Python code into a web app. And so let me show you how it works, like the main paradigm. I've used this before to create a debugger where you give it some Python code and then it debugs it for you via web UI. So here, so let's say people go to your website and then they route to the predict class, then it's basically going to be like, okay, well, I need to get a specific example. And then, okay, I'm going to get the sentence from the request. And then I'm going to make a prediction. And then I'm going to return the probabilities to the user. And then I'm going to return it as a JSON because that's like what the web servers understand. And so that's pretty much it. Like you see, like it almost becomes trivial for you to, if you have a machine learning project that you've built, if you want to turn this into a web app, it's very easy. Well, the hard part is making sure that the model gets continuously retrained, that if it fails, it can recover gracefully. So these are all systems problems, and I actually cover how to deal with more of these systems problems in my system design primer video on YouTube. So make sure to check that out if you're interested in how to do the DevOps side of machine learning. But you can see here, like it becomes like this. Like really, imagine you create a dictionary, right, of all the things you want to return to the user, and then you just call JSONify on this dictionary, and then people can just do whatever they want with it. So yeah, it's not complicated to do this stuff, and you can sort of test it out by yourself. Like you can actually bind a specific UI to some code, and then give it a specific number of workers. So let's say you want to run this on four cores on your machine, and ideally this is elastic, right? Like the more users you have, basically, the more users you have connected, the more cores you want to have, and so that's why cloud is good, or having like your own compute in case you're worried about like being canceled or something like that. So that's pretty much it. I hope you enjoyed this. Like, I think to sort of cover the main ideas of this book, there's sort of, I think, like a few core ideas. So, one is like setting up your environment. The second is the differences between supervised and unsupervised learning, how to cross validate your data, and why that's a good solution to prevent overfitting of your data. When you're trying to measure what overfitting is, like you basically have a features that you can compute automatically, a metric from precision to recall to precision at k. How to create your own features and select them either by looking at variances or what's important, data imputation, bucketing your data. How once you have a certain model that you're pretty dead set on, you can essentially put all the hyperparameters in some nested for loops. Why working with images is very easy to do with a library like PIL, which turns an image into a matrix. Why working with text is very easy because you can turn a body of text into sentence vectors. Once you have a bunch of models, how you can ensemble them, and then how you can turn your work into a web app. So if this was interesting, make sure to check out my other videos. I have a lot of videos that discuss how to work with machine learning. Especially check out the speedruns. I think are very useful if you want a crash course into machine learning. So thank you for joining, everyone. I really appreciate it, and thank you, Hector, for all the good questions. I appreciate it. Thank you so much.